Hello everyone. Now, after the theoretical background of CNN, now I'll show how will we actually can implement CNN. So I'll be implementing CNN in MATLAB. So it's pretty easy. So implementation of CNN comes in four different steps. In first step, we'll load the data. That is our training data and our test data along with their classes. Um, Along with their yeah along with the classes, and in the next step will form an CNN layers. Then in the next step with the training data and with the layer defined, and alongside we'll define some training options. Based on that we'll train a neural network, and in the last step we will with the trained neural network will pass our test data and check whether the class that we get matches with our actual class or not. So let's start with loading data. So first let's say we have x x train data. Let's say its dimension be n cross row cross height. So let's say the dimension of x train be n r cross h. So basically we have a n number of r cross h images. It means that, and corresponding to this in uh, images we have their different classes. So its dimensions are n cross, let's say 1, in classes corresponding to n datas in x train. So this x is our data and their corresponding classes are stored in x train. Normally these in y train, sorry, and the classes are usually stored in category in stored as data type categorical. So after this x train and y train we have another set of data for x test. mm, let's say its dimension be m cross r cross h. Please note that the dimensions of the x train and x train and x test must be same. So this is basically is n sorry, it's m number of r cross h images, and corresponding to this y test we have m its dimension is m cross 1, that is m, that is its classes correspond to m data in x test. uh, After this now we'll define the, so what we have now, our x train, y train, x test and y test. So we'll train the network based on x train and y train. Then whatever network we get will class will utilize x test to pass through that train network. We'll get a corresponding y predict. Now for accuracy we'll compare whether our y predict matches with y test or not. So this completes our loading data segment. So in the next step we will show uh, define CNN layers. Wait a second, let me close my remote. My battery will shut down. So for a CNN layer, we will define our functions now. Okay, we can define as this layers equal to, okay, let me keep the slide, I mean what layer comes after what in the side. Wait a second, I use somewhere. Oh, wait a second, let me open the slide so that like I can use it as a reference to make some. Where is it? Where is it? I mean, I just need to. I'll use this um, um, drawing to just to check which layer comes after what. Okay, wait a second. It's too clumsy. Let me open a separate one. Where is it? Oh, where is the layer? Where is the? Okay, it's in my report. Okay, anyhow, like I'll dictate and keep on going. So for the first, we have image input layer. That is our input layer. Uh, mm, uh, so each so what I said, the size of each train image is r cross h. So what we'll do, we'll write over here as r comma h comma 1. Now we need to define some other parameters also. Name as I will write data, sorry, then we'll write data augmentation. For data augmentation we'll set as none. Then next comes our normalization method that we want to use. Normalization method, it comes as sorry, I need to put it inside this marks, sorry. Normalization methods will be the zero center, like how is the method like how should we normalize them. So basically it says that we'll normalize in a such a way that the mean should come near zero. Then so here defines our, so here we have completed definition of our input layer, right? Now next we have this convolution layer. Convolutional, how much battery do I have? Convolutional 2D layer. Let me, please wait a second. I'm running out of battery. I need to bring my adapter fast. Okay, so in convolution layer, uh, now we'll define convolution layer. In convolution layer, in the first convolution layer, each filter size are of 11 cross 11, and there are total 30 such layers. We can give this convolution layer as a particular name. Let's say as con1. Then comes number of channels. It's um, 30. Then we can also define how much stride it should take in the two dimension. It's 1 space 1. Then we can use some zero padding uh, in the input layer image, so that so that the convolutional filter can treat the corner points as the mid center of its filter. uh, padding, there's no padding. Okay, so that's right. Okay, so here we have completed our building the convolution layer. Okay, so you can see what first is the input layer, defined input layer. Then next is define first convolutional layer. So here's a one thing I'd like to mention is that sorry, the number of channels should be 1. See, the the third dimension of the input layer is 1, then the number of channels should be strictly 1. So basically the number of channels for any layer of a CNN is dependent upon the number of component used in the previous layer. Since each image R of R cross H and the number of channels are so the number of channels in the input layer should be same in the third dimension, should be same as the number of channels um, for the next layer or the first convolution layer. So after convolution layer, now we'll define um, called ReLU layer. ReLU layer is basically it scales everything in negative as 0 and keep the positive as it was. So we'll name this ReLU layer as some ReLU 1. Then after this we can use some cross channel normalization techniques to reduce everything from 0 to 1. Normalization. Whoa. Then we can define to like the particular value of the user scheme method to normalize. Then after uh, okay, let me comment out here. It's activation function is ReLU, and for this one is normalizes to 0 and 1. Okay, after normalization layer we have max pooling to the layer. As I mentioned before, what max pooling layer does. Max pooling layer basically it's picks up chunks of adjacent pixels and based on that it to vote out the majority of them. It is done just to reduce the dimension and for simplification of the calculation while training a network. So in max pooling 2D layer, so how many max pooling layers are there in the uh, in this? So we have as name, then we have as uh, we'll give a name as what, pool 1, then was the stride it will take, it's stride. Stride means like uh, at what's the step number in each step it will traverse through the previous layer. uh, then we can use a padding also here. Padding will be like, you can mention it as, since it's a 2 cross 2, so we'll be using 0 by 0, 0, sorry, 0. After this, okay, right has unpulling outputs. Okay, while training we don't want how many unpulling, these are the parameters. Mm, so so now the same thing will be repeated again from the convolution layer. Whatever you get over here. So but thing is that number of channels 20, what should you do, how much should you pick? Okay, so in for the second convolution layer, what we'll choose filter size as 5 uh, 5 comma 5, sorry my mistake here, also it should be a comma. Then number of filters, like we can keep it 30, or if you want we can reduce it to 20. Then name, will mark it as the second convolution layer, we can't have same name for both of them. Then number of channels, so number of channels is, in this case, is 30. Do you know why? Because the number of filter, how it was in convolutional 2D layer for the first convolution layer, the number of channels was depend on the number of last dimension for the input layer. Similarly, the number of channels for this layer is depend on the number of filters used in previous layers. If here it's 30, it should be 30. So now the stride is another question. You can use 1 cross 1 padding or whatever it is. Then you can it's second convolution layer. Then the same thing, you have your rail loop, but the name will be different. Then we have cross channel normalization layer. It's the same. You will give it same. Then we have a, this is max pooling. Previous one was max pooling 1. This one will be max pooling 2. So after this, what we'll do, we'll add one more convolution layer. Convolutional 2D layer, right? Okay. Convolutional ReLU. So for this one, like we can use 3 3 20, and the number of channels will be how much, 20. Why? Because the number of filters in previous layer was 20, so number of channels in the next layer will be 20. Stride, you can keep the same relu layer, it should be relu 3, and like we have, since we have already reduced the dimensions, so usually if you apply feed a 100 cross 100 100 cross 100 image, like by the time it reaches max pooling over here, it reduces 3 cross 3 approximately 9 times, around 100 by 9. So here by the time you reach over here, it will reduce even further more. So that's why we won't introduce the cross sorry max pooling layer over here again. So from here either you can use it, but I mean the same pattern will be repeated over here again and again. um, Now we'll jump directly on to, I mean if you want, if you can still add 2 or 3 more convolution layers over here. So next we'll design after this a fully uh, connected layer where each fully connected layer has 4096. It is the 4096 neurons, and it is the most what should I say, the most important layer, because all the features that has been extracted for all the for all the neurons or all the convolution, all the 3 convolution layers that we have defined so far are being stored to the fully connected layers, and from fully connected layers only we can actually get a wide spectrum of these features. So fully connected layer we can give a name as FC1, let's say. Then there are different factors as the weight learning factor equal to 1. Okay, these are the some statistical things which are associated with the weight change algorithm that I have explained in my previous video, I mean, or in the CNN presentation. If you remember, I have explained something about the back propagation algorithm, like so based on weight learning factor is also associated with the back propagation algorithm, which basically determines at based on the error that we get at the output layer, and each of and corresponding error that propagates to each of the neurons for the hidden and the output layer, at what rate the weight should be changed, it has something to do with that. So another thing is you can also define weight L2 factor too. um, it's 1. Then something we have called bias learn factor. Uh, you know what is bias? Bias means something. A bias learn factor is the rate at which the we can change the bias. I mean the weight associated with the bias is, suppose if we have an equation as something a dot x plus b. Sorry, let's say we have an equation ax by plus c. Okay, we have is ax plus by plus c equal to 0, and each of these coefficient for x, y, and the constant are fed into into a neuron, right? But these are not fed as direct input, always a weight are associated with it. So similarly, when c is also fed this constant, when it is fed to a neuron, uh, it is some kind of weight uh, are added to C, then only it is being fed into the neuron. So when we uh, change the weight using bias, using the back propagation algorithm, so this bias learn factor is something which deals with how to change the change weight of the link that connects with bias like C with the neurons. So this is bias learn factor. So after bias learn factor, we have something called bias L2 factor. That will be 0. Then again we can use another more ReLU layer too over here. Suppose ReLU, let's say so far ReLU 4, ReLU. Let's say we can define over here name as, sorry, we'll write a name as ReLU 4. So have I given a comma over here? Okay, I haven't given. Give. Then apart from this, we can use an dropout layer also. That sounds very interesting. Like we are using neuron to train them, and we are again using some kind of function to drop neurons. Okay, let me tell you about dropout neuron. Dropout neurons, because since most of the features are already stored in the fully controlled layer, so when it tries, when the network try to gain a particular pattern, uh, so dropout layer are mainly used in this case to have, to draw few neurons when the network reaches a stagnant position, to so that the neurons don't get overtrained. It's a very complicated process. uh, so basically in short, these are dropout layers are given to avoid overfitting. Like when you are really not getting any accuracy, this dropout layer won't work. But yeah, trust me, when if you define this layer, when it reaches around mm, close to 100% accuracy, so if you at the time if you train more and more with like same kind of data set, your neurons might get overtrained. So in order to uh, save your neurons from getting overtrained, we should always use a dropout layer. Then again we have something called the same thing we can repeat again. Like if you observe, like most of the CNN I have seen, there are always there are two convolution layers. Sorry, not this one, this one. Mm, so there are two fully connected layers, but you can use multiple convolution layers. You can change their filters, I mean based on your experiments, based on your trial and error method, you can change the parameters. But fully connected layers, like if you really think of changing this 4096 to let's say 1000 or something, like you might save time, but at the same time you are compromising with the accuracy of the network. Yeah. Yeah, yeah, yeah. So after this, next will be our soft max layer. It's something mm, more or less like um, basically if you have 5 different classes, so in soft max layer it basically says whatever output you get until this layer. So so based on the output that we get until this layer, based on that it will say what is the what is the probability of each class as the outcome at this layer. Okay, I'm not. I think I'm explaining in a complicated way. So basically, if you have five different classes, and based on whatever output you get until this layer, in softmax layer, it will predict like for each classes what's the um what is the percentage what is the percentage probability for each of the classes, each of the five classes to be as outcome from this dropout layer. So after this we have the classification layer. So the classes which has majority in probability, that which has the majority, or I mean the class which whose probability is maximum at this soft max layer, that class is particularly classified as the output name. Your output. So far these are the steps that are done to build a neural to build in layers of CNN. What is okay? So let's say if I define over here 100, and over here if I define as 100, I don't have an right now I don't have any data set to show you. Okay, I'm getting an error, but trust me, it worked. And I haven't, yeah, right now what I was saying, like I have a video demo of how each of these layers worked while I was doing my project on motion recognition, but due to some like rights of the, I mean due to some legal issues or something, like we are not allowed to save those data after we like after we are done with that class. So that's why I can't show you the demo, but like yeah, I do have those videos I can share with you. Convolutional, okay, it's sorry, it's convolution, it's not convolution, it's not convolution. Be careful with this, like convolution. Okay, fine. Now we'll run it again. What? They can't find, okay. They can't find Relu. As if I have given nickname to it. Uh, layer, layer, sorry, layer, layer. Okay, now what we'll do? Uh-huh. Line 59. What's not working? For which line number 38, right? Mhm. Line number 13. Okay, I don't know. I need to go through this, but yeah, this is how it work. So, I mean, I have just 1 hour to show the demo, and so that's why I need to move fast. However, I'll show the demo later on. So after you are done with your defining the layers of a convolution layer, now we have to define the various parameters to be used to train the network. Options is equal to, you can write is as training option. So first will be the sigmoid SMGDM. I mean, this is something like what I said, like why use the sigmoid curve, so that differentiation of a sigmoid curve uh, doesn't doesn't give us the infinity error. I mean, I have shown in my previous slide also the same thing. Then we can schedule the, how we want to schedule the learn rate schedule. We can set it as piecewise or global, whatever you want. There are many such things. Then after this we can write learn rate drop factor, the one I told that uh, that to prevent overfitting sometimes we need to drop some neurons from our network. So it's something uh, is related to that. Just like weight learn factor, there is learn rate drop factor too. Then after this we have maxipos, like maximum iteration. It should run for one complete data set. So after this we have sorry, I did something wrong. Okay, now we have mini batch size, like the training data are usually they are uh, segmented into multiple smaller segments, and they're to reduce the training time, and also to work the to make the model work more efficiently. And like during a training, if you want to visualize the stats, like for that also we have something called plots. And we can write it here as training progress. So these are training options done. I don't know why I'm getting in there. Okay, anyway, so after the training options are done, now what you do, will train the network. So let's say network equal to, we can use train network. Is it so? Let me check once. Edit. Oh, sorry, it was just train, I think. Train, you'll pass on your data sets. Xtest, was it Xtest? Oh, sorry, Xtrain. Oh, sorry, my mistake. We are trading, right? Here comes train. methods. Mm, training options. Now you can use text train. You have to pass their corresponding what their classes to. Then you will utilize the options. So after you get a trading network, now we'll classify them. So what will they use? Y. Sorry, I'll write it later on. We'll use a function of classify. There you need to pass the. This is our trade network. This trade network when it passes. What is that now? Okay, classify equal to. We have as command C. We'll pass the network. Then after network, we'll pass the test dataset, and based on the train network and the test dataset, we'll get something called Y predict. So whatever Y, now we'll check whether Y predict uh, matches Y test or not. So based on that, we'll get the accuracy. So here we all have the code. I'll send you some more demos on like how to like what method I use for my project and all. Thank you.